Hello? Today we are considering the structure of the atom, but let's look at the atom inside more succinctly, more complexly, how the atom works. In fact, the establishment of the structure of the atom was a rather long historical process. Initially, it was known about how an atom works, that it has a nucleus that is positively charged. This was evidenced by Rutherford's experiments, and initially it was thought that the electrons were located as if in a mixed state, for example, between the nucleus and the electrons wedged into the total mass of such an atom. This is the so-called pudding model. Then a planetary model appeared in which electrons were considered as some kind of planets that move around a conditionally core, which was considered like the sun. But then, taking into account modern requirements for the structure of the atom, taking into account the fact that this was proved and calculated theoretically and proved practically, it turned out that the atom is quite complicated, and in it, from the point of view of chemistry, the most important role is played by the location of the electron particles. How are they arranged in an atom? So if we imagine that an atom consists of a nucleus inside, we recall that the nucleus has a positive charge, since there are proton particles with a positive charge in it, and neutron particles are also located here. But these are the main particles of the nucleus. In fact, there are smaller particles in the nucleus, but they are not the main particles, although they are part of the nucleus. Where are the electrons located? Electrons can be placed at levels that are located around the nucleus. I have shown these levels here in circular orbits. The electron may be here in this case. Let's say it is the electron that is closest to the nucleus. There may be two such electrons here. Then the electrons can be located further from the nucleus, for example, at the second energy level, at the third level, and at each energy level there is a certain arrangement of such electron particles. At the same time, the closer an electron is to the nucleus, the retention energy of such an electron will be the largest. That is, such an electron cannot leave the atom very quickly. This requires a lot of energy, ionization energy. Then the electrons which are located further away from the nucleus are held by the nucleus already weaker, and accordingly the electrons that they are at the last energy level. They will be held by the core weaker. So it turns out that there are concepts of energy levels in the atom. These levels, or so-called layers, are sometimes called that. They are located around the core. Each of these layers has a designation. This designation can be either a number, the first level, the second level, the third level, or these levels can be indicated by letters. Then the first level is indicated by the letter K, the second L, the third M, and so on in the English alphabet, the Latin English alphabet. That is, then it turns out level 1, it's labeled K, level 2 is labeled L, level 3 is labeled M. The fourth is labeled N, the fifth O, the sixth P, and the seventh is denoted by the letter Q. So this is the designation of levels, and the numbers that are written in front, they are denoted in a general way by the letter N, and this is called, this number, the principal quantum number. And it's denoted by the little letter N. The principal quantum number. Okay, what, knowing this number, can we calculate? We can use a formula in which we can determine how many electrons can fit at each energy level. Substituting the number of each of these levels instead of N, we can calculate the maximum number of electrons at each level. Let's do this for the first 4 levels respectively. N, this will be the maximum number of electrons at a given energy level. Then substituting, instead of 1 we get 2 electrons. Substituting for the second level, it will be 8. At the third level it will be 18. At the fourth level it will be 32, and so on. If we are talking about the 5th, 6th and 7th, then of course the number of electrons can be higher there. But so far the atom is so organized that there are no more than 32 electrons on one energy level. Now, what else can be said? The fact is that in addition to levels, there are sublevels, and they're labeled by small letters, which we can use in this case for each energy level. They are S, denoted by P, D, F, and so on. Then a certain number of electrons is also placed on each of the sublevels. For example, only 2 electrons can be placed on S sublevels. This is written down with the notation S squared like this, but read S2. Then on the P sublevels, the maximum number is 6. It's written like this. The D sublevels are 10. And on the F sublevels, it's 14. And this is also written as follows. It's not hard to see that the difference between neighboring sublevels is always 4 electrons. Then we can predict how it will be in the 8th period. For example, what will be the number of G electrons? There will be 18 of them. Now let's go back to our maximum numbers at each level and explain. If there are only 2 electrons at the first level, such electrons will make up the S sublevel. For the second level, S2 are first, followed by P6. For the third level, S2, P6 followed by D10. For the fourth level, it is S2, P6, D10, and respectively F14, and so on. It is not difficult to see that there is a general pattern here. We can see that the S electrons always come first, and what these electrons are and how they move around the nucleus and what is the shape of electron clouds, we will respectively discuss this point with you in the next lesson. But in addition, I would like us to learn how to determine how many levels there will be, respectively, for this particular chemical element. Let's take, for example, the element nitrogen. Its serial number is 7. And it can have 2 electrons on the first level, according to our scheme, and these will be S electrons. And on the second level, it will have 5 electrons, because there are 7 electrons in total. So how many energy levels does nitrogen have? As we can see, we have 2 such levels. And let's see that we have nitrogen in the second period. So the number of levels coincides in this case with the period number, but maybe it's only nitrogen that has this pattern. Let's take the element phosphorus. Its period number is 15. It will have 2 electrons at level 1. It'll have 8 electrons at the second level. And the last one has 5 electrons. So phosphorus has 3 levels respectively. And it's in the third period. From this, we can easily conclude that respectively, the period number will always show how many energy levels there will be. And you can predict this for any chemical element. For example, iron is in the 4th period, so it will have 4 levels. And let's say the element francium, the most active among all metals, is in the 7th period, and it has 7 energy levels. At the same time, I note that the farther the electrons are from the nucleus, the more easily the elements will give them up, because the attraction to the nucleus will weaken. But besides the fact that we have given you the pattern of the period number and the number of levels, let's see. We have nitrogen with 5 electrons at the last level, and nitrogen is in the 5th A group. Or in the 15th group in the semi-long version of the table. But phosphorus also has 5 electrons, and we see that it is also in the 5th A group or in the 15th group in the semi-long version. Thus, it turns out that nitrogen and phosphorus are not accidentally in the same group of the periodic table, since they have the same number of electrons at the last energy level, and this number is equal to 5. Thus, it turns out that the group number also carries information about how many electrons will be at the last level for a given chemical element. This number cannot be 8, despite the fact that the group number is the 15th. This does not mean that there can be no more than 8 15 electrons. Thus, by looking at the last group number, you can determine how many electrons a given chemical element will have at the last level. Thus, it turns out that the periodic table of Mendeleev, the numbers that you can observe there carry a certain load. First, by the ordinal number, we can determine the number of protons, electrons in an atom. By atomic mass, these are protons together with neutrons. By the period number, we can determine the number of levels and predict them for a given element, and then distribute the electrons so that they are distributed at each energy level in a certain way. And we can look at the group number to predict how many electrons an element will have at the most recent level. That is, each digit in the periodic table of Mendeleev carries a very important meaning concerning the structure of the atom. Goodbye.